So the last topic we have to talk about in the relationship between two quantitative variables is looking at the idea of correlation. So first, the symbol wise here, R is used to represent our sample correlation, and the Greek letter rho is used to represent our population correlation. So for our understanding, we're pretty much only going to ever see R because we're never going to have our entire population. Now the goal of a correlation is to measure the strength and direction of the linear relationship. Remember that we talked about we're only going to focus on straight line relationships in our course, but there are other types of relationships. So correlation is only something we should look at for a linear relationship. And then it gives us two different things. It gives the strength as well as the direction of the relationship. It indicates how close our points are to that predicted line. And when we're talking about that predicted line, we're talking about that y-hat equation. So if I put that line on my data set, how close are those points to that line? One of the things that we like about correlation is that it has to fall between two numbers. Correlation always has to fall between -1 and +1. And depending upon where we are, we get some information about our data set. Let's first talk about the direction. So we're talking about the direction of the relationship. We're talking about the direction of the slope. Is there a negative slope? Is there a positive slope? Or does it really seem to be a straight line, flat horizontally, where there's really no slope? The same idea comes over here to correlation as well. If I had a negative linear relationship, I'm going to expect my correlation will also be negative. If I have a positive linear relationship, I'm going to expect my correlation to also be positive. Versus if there's no linear relationship, I'm going to expect my correlation to be close to 0. So really the sign of correlation tells us the same thing as the sign of the slope. So in a sense, we're not really getting anything new when we're talking about direction for correlation, because we should have already seen that in both our scatter plot when we've looked at that, as well as when we've calculated our slope as well. So we really already have the direction in those two different ways. So what we really like correlation for is to help us with the strength. And so what you see a graph of here is where we have to be between -1 and +1. And depending upon where we fall on this scale, that tells us about how strong the relationship is. The closer we are to either extreme, whether it's -1 or +1, that is going to be a very strong relationship if I'm close to those extremes. Now, just as an aside for comparison, if I had a correlation of exactly 1, this is what it would look like. I would have my line graphed. It could have a positive or negative slope. That part does not matter. But then every single point would be on that line. So that's why very seldom are you going to see a correlation of -1 or +1, because generally our points are not all going to fall perfectly on a line together. But if I get a correlation that's either close to -1 or close to +1, that's going to be a very strong relationship. First, if I get something close to 0, keep in mind that 0 means that there's no linear relationship. This is going to be a very weak relationship if I'm close to 0. And then this value itself, we will not be doing the calculation for. We will just be getting that value from Statcrunch. But before we actually do that, let's try to understand correlation by looking at some different pictures we have here. So looking at these 4 graphs, we're going to go through each and sort of talk through correlation for each of them. So let's first just talk about what kind of sign we would expect. For graph A, since I have a positive slope, I would expect a positive correlation. For B, since we have a negative slope, we're going to expect a negative correlation. For C, it looks like a positive slope there as well, so I'd expect a positive correlation. Versus graph D here, is not a linear relationship. So technically, I shouldn't even be calculating correlation for this graph. But my software will do what I ask it to do, so it still will calculate a correlation for this graph. But because I have this curved relationship, I'm going to expect a correlation close to 0 for this one. Now, so let's actually compare graphs A and C, since they both have a positive relationship. If I look at putting a line through these, which I could actually do here for demonstration, so kind of imagine I have my line going through my two graphs here. Correlation is measuring how close those points are to that line. So I look at graph A, those points are all really close to that line in comparison to graph C. In graph C, there's a lot more scattering going on away from that line. So I'm going to expect a stronger correlation for graph A than I would for graph C. So let's actually show you what we get for those two. Well, for graph A, it's not this where every single point perfectly falls on that line, but they're not too far from it. So I'm going to expect a correlation relatively close to 1. And in fact, from Statcrunch, I got 0.931 for that graph. For graph C, again, we said we knew it should be a positive relationship, but it's not near as strong as graph A was. This one turned out to have a correlation of 0.483. All right, so now let's go ahead and move over to graph B. Graph B will have a negative correlation since it has a negative slope. Looking at how close the points are to this line, well, they're not as close as graph A, but they're not quite as far away as graph C. So notice the points are overall a little bit closer, versus I have some here that are much further away from that line. So this correlation, strength-wise, will be between those two values, but it's going to be negative. So for graph B, when I got its correlation, it was negative, just as expected. It was negative 0.712. All right, for graph D, again, we expected a correlation for this one pretty close to 0. I didn't get exactly 0. I got 0.032. Now, if you're feeling uncomfortable with correlation, there is a nice little app actually out here on Statcrunch. So if I just open a blank Statcrunch screen, I can go to applets, and there's this correlation by eye. And you can just use the randomly generated, so just you can kind of hit compute here. And it's going to create a scatter plot. And then you can look at the scatter plot and try to guess what that correlation is going to be. So for example, with this one, it looks like it's positive. It's not real strong. So I'm going to start with maybe like 0.3. And then I can check it. And it says, okay, try something stronger. So what is stronger than 0.3? Well, it needs to be closer to 1. So I'll try 0.45. And it tells me to try something even stronger. So let's try 0.55. All right, now it says we're within 0.1. I can hit the show, and it'll tell me exactly what it is. So I can hit simulate to get a new one. So if I look at this one, here's a very negative correlation. I kind of have this outlier up here as well. So I know it's going to be negative. It's pretty strong besides that point. So I'm going to say it's negative 0.8. And it says that we're within 0.1, and so I can check to see what it actually was. And then you can also add some points here yourself. So if I want to see, well, what would happen if I added another point out here? So I could say that'd be about 17 and 20. And we add that point. You can see what a drastic effect that would have on the correlation. You can actually start with just a blank one too and kind of add points on it. So here I'm trying to get one that's pretty close to -1, as you can see here. If I just throw 1 point out here, it's going to have a big effect on that correlation. So just a nice way, if you're feeling uncomfortable with correlation, to play around with it a little bit. All right, the other thing we can talk about when it comes to strength and the idea of correlation is this thing called coefficient of determination, which is just our correlation squared. So since our correlation is between -1 and +1, when I square a negative number, it's going to be positive. So the smallest value our squared can be is 0, and the largest it can be is 1. So since squaring negative values gives me a positive value, I'm really losing that information about the direction. So if I'm looking at r squared, I can't tell you the direction of the relationship. But I already have that in a couple other places. I have that with my scatter plot. I have that when I talk about slope. So I really should already know the direction, even though I don't have that information with r squared. It indicates the strength of the model, not the appropriateness. So what I mean by not the appropriateness is, for example, I could have a graph that looks like that. And hopefully if you look at that, that actually looks curved. But I could still fit a straight line to it. And so if I just look at that coefficient of determination, it's probably not going to tell me that I shouldn't have fit that straight line to the data set. So I need to make sure, by looking at my scatter plot first, that I should have created a straight line pattern. What we like about it is the interpretation. It's the percent of variation. And when we're talking about variation, you can think about the idea of differences. That can, in y, that can be explained by x. So for example, house prices are different, right? But maybe a certain percent of that I can explain just by looking at how many square feet that house has. It's not going to probably explain all of it, but it's going to explain part of what's going on with why those house prices are different. To understand this better, let's actually do this for our example. So for our football data set, I'm going to the same place we had already been, that regression in simple linear, putting in our x and y that we've already talked through before. And I get that when I initially have my compute. So here is that r, and our r squa is your r squared. So these two numbers are just what our r and r squared are. I'm not going to have to worry about doing the math for them. They are just there for me. All right, so I've just written those numbers down here for me, and then we can focus on interpreting these numbers. All right, so if we're looking at just the r, what I first know from this is that it was positive, which doesn't shock me. I already knew that. Now, how strong is it? Well, it's not super close to 1, but it's closer to 1 than it is to 0. So I probably put it somewhere on the strong side of things. So I might just say it is somewhat strong. Maybe now you'll see why we like r squared. So the first thing I'm going to do is take this decimal and change it to a percentage. So I do that by just multiplying by 100%. And so I get 49.65% of our variation in y, which was points scored. Can be explained by our x, which was total yards in the game. So about half of why they scored a certain number of points, I can explain by looking at total yards and nothing else. I'm not looking at penalty yards, I'm not looking at time of possession, I'm not looking at turnovers or anything like that. So by looking at just one thing, I can explain about half of what's going on. That might not be too bad for me when it comes to trying to explain what's going on with football. Right, so that takes us through correlation and the coefficient of determination. In the next video, we're going to do an example of putting everything together.